I'm going to try to talk to you about something technical, domain-specific languages, and some of you are listening via translation. Thank you to the translators. Hello, guys. So I might say something you don't understand. You will then help me and help yourself and help the rest of the audience if you ask your questions. Or will you guys ask questions, please? Good. Okay. And don't be afraid to nod your head or shout or look puzzled or raise your hand or any of those things. Good. Are there any questions? Not yet. Okay. Not yet's a great answer. Thank you. Oh, I took my jacket off. I started with my jacket on and my hat on to look nice, but I'll be too warm. I'm going to take them off. Okay. Right. So they asked me to speak about quoted domain-specific languages, and I'll do that. I'm going to slip in two quick ads first. So I consult for a firm called IOHK. They do cryptocurrencies. Most people stay away from cryptocurrencies because they're highly volatile. But the peso, so you guys might find them more interesting. IOHK, there are a huge number of cryptocurrency firms. IOHK is a very interesting one. Unlike any other firm on the planet that I know of, they actually make use of peer-reviewed research. That is, their goal is everything they do should be published as peer-reviewed research. This is sort of how science advances. So they're trying to exploit that because it's very difficult to get all the cryptography and other things in cryptocurrency right. So they're trying to get that right. And also they've written most of their software in Haskell. Who knows what Haskell is? Who doesn't know what Haskell is? Okay, very good. They've written most of their software in Haskell, a functional language that I contributed to the development of, so I'm excited about that. And they have this cool web page showing you the game of life, which has now gone dead. Oh, well. So you can ask me questions later about IOHK, but I'm not going to talk about that. Let me show you something else I'm not going to talk about. Oh, no, that's what I am going to talk about. This is the other thing I'm not going to talk about. So I've just written a textbook. And of course, having just written a textbook, I'm really excited that I just wrote a textbook. It's about Agda, which is sort of what Haskell wants to be when it grows up. So Agda is a functional language very much in the style of Haskell, but it's total. That is, you are only allowed to write programs that terminate. It just checks that everything you write is a structural recursion, which is a pain if you want to write something like quick check, which is not a structural recursion. But because everything is total, you can use it not only to write programs, but also to prove theorems about the programs. So one of my standard talks, which I won't give you, is I show you how to define the natural numbers, how to define addition, and how to prove that addition is associative, which is really cool because if you think about it, there are an awful lot of natural numbers, right? And proving for all of them that addition is associative is a very neat trick. And you can do it in just a few lines in Agda. And as always, trying to get a computer to check your proofs is, how do I put this? Well, I could say highly annoying, but that wouldn't express how frustrating it is. But it's also like a video game when the proof actually goes through, you're all and really excited, and you get a release of pheromones. So I'm not going to talk about this, but the book is available online. It's an introduction to Agda and then an introduction to formalization of programming languages. So Lambda Calculus, as you'll hear me talk about, is the absolute core of everything we do. And this shows you how to formalize and, again, prove properties about Lambda Calculus. One of the nice things I discovered while writing the book is that if you prove the standard thing about Lambda Calculus, which is called progress and preservation, you get for free an evaluator because we're using intuitionistic logic rather than classical logic, which has strong properties. So it's really fun. And you actually get an evaluator for free. It's a very slow evaluator, but you get an evaluator for free. Okay, that's all I'll say about that. Are there any questions now? Still not yet. No questions about that. Oh, I'm sad. Okay. You can also ask me questions over the breaks. I'll be around all day. And at the end of the talk, I will try to leave some time. Okay. No, that doesn't work. This works. 3 fingers. This is called BuzzConf. Okay. No. There we go. All right. So here's what I am going to talk about. Quoted domain-specific languages. This is work done by myself and many colleagues. I'll show you who they are at the end of the talk, but this isn't all my own work. And it's, let's see. How many people know what Haskell is again? Good. How many people know what Lambda Calculus is? How many people don't know what Lambda Calculus is? Good. Okay, so I'll explain that when I get to it. But Lambda Calculus is the theoretical foundation of all functional programming languages. How many people know what a domain-specific language is? Okay, and how many don't? Good. Okay, so keep raising your hands when you don't know. That's excellent. So what a domain-specific language is, it's sort of in the name. It's a language, programming language that's specific, that is designed particularly for using in a domain, that is an area of use. So there are lots and lots and lots of different domain-specific languages out there. What I'm going to show you is, so for instance, we have a financial domain-specific language for the blockchain just for writing certain limited kinds of contracts, and that's one of the things that Simon Thompson works on. It's called Marlowe. So he's going to also talk to you about something completely different. But Simon and I are actually colleagues at IOHK, and we work together on this domain-specific language called Marlowe just for writing contracts. So it's not Turing complete. It can't do anything a computer can do, but it's very good for writing certain kinds of contracts. What I'm going to show you is a domain-specific language for querying. How many people have heard of databases? Good. How many haven't? Good. How many people have heard of SQL? How many haven't? Right, so SQL is a query language, and it's just designed for writing queries against relational databases, and that's it. So how many people have had to interface their Java or JavaScript program to SQL? They write some SQL and then okay, and how many haven't? Okay, so for those of you who haven't, it's the ones who have can tell you it's painful. So the question is how to make it less painful. And the idea is I'll just use one language, but it will be able to interface very neatly with queries. And that's what I want to show you. So it's how to embed in your larger programming language a small programming language that's just for doing what you need to do. So what I'm going to be showing you is a technique for doing that. I'm going to explain it for databases, but I think it works for many, many other things. So that's why they chose for me to explain this one to you. Because how many people actually might need a domain-specific language for something? Like need to make their own for writing games or doing finances? Okay, so a tiny number of you are raising your hands. But I'm guessing that if you knew a little bit about domain-specific languages, you will bump into lots of problems where you go, oh, I want a domain-specific language for that. There's a whole school of research. The Racket people. How many people have heard of Racket? Right, good. So Racket is a very different functional programming language. It's also great, but Racket is just optimized around designing your own programming language. So whatever you need to do, let's design a programming language for it. Great, we're programming language people. What is the answer to your problem? It's a programming language. What was your problem, by the way? Let me show you how to do this. Right, this is my daughter. She's older now. But the thing on her head, how many people know what that's called in English? It's called a fuzzy thing. We call it a smuffy. And when she got a little bit older, she decided that I needed a smuffy. So she made some smuffies for me. This is my Lambda smuffy and my Pi smuffy. So Lambda, as I said, is the underlying theory of programming languages. And very often, Developers, when they hear the word theory, they go, oh, that's too hard. That's not for me, right? I don't talk about theory because that will make my life more difficult. So the most important thing you can take away is, right, and then they think of lambdas, right, as hard, right, which is wrong. So think of lambdas this way. They're fuzzy. They are cuddly. They are your friends. Right? John Arbuthnot said, if you can apply a mathematical theory to something, and you do not, it is as if you are searching for something in the dark, and you had a candle you could use, and you did not use it. Okay, so you can think of lambda as your fuzzy friend, or you can think of it as your candle in the dark, something to guide your way. So I'm going to show you one example of that, which is applying ideas from Lambda Calculus and other simple calculi to design domain-specific languages. Right, so here's our question. How do you integrate a domain-specific language into host language? And I'm going to show you two tricks for doing this. And they're really old tricks, which is why the name of the talk is Everything Old is New Again. So one is just the idea of quotation, which you can find in McCarthy's Lisp back in the 1960s. And the other is the idea of normalization, which you can find in Genson's proof of cut elimination from 1935. Okay? So that's 85 years old and 60 years old. Not quite 60. Right. What is a functional language? A functional language is a domain-specific language for creating domain-specific languages. Right. The best, as I said, very often the solution to your problem is another language. So you want to be easy to implement that language. That's exactly what functional languages are good for. The thing that functional languages are best for is designing and implementing other languages. They're perfect for that. And in particular, sometimes you just do a standalone language, right? You say, right, I need this language, here's the parser, here's the compiler, here's the type system. You design everything from scratch, and you work with it from scratch. That's kind of how SQL works, right? SQL is just a completely different language. And then you take whatever you want, and you often, right, you turn it into a string, and you shove your string out of JavaScript or out of Java into SQL, and it parses it, and then goes off and executes the query. So you can have a completely standalone language, but what people often do is they embed their domain-specific languages. So basically that means it's a library. So sometimes you can think of domain-specific language as a fancy word for it's a library. But usually there's language-like constructs within this library. Okay, so it's how do we reuse one general purpose language like Haskell or F# for doing something else. So by the way, I'm going to be showing this in F#, not in Haskell. How many people know what F# is? Good. How many people don't? Good. How many people know what Microsoft is? Good. How many people don't? Right. So Microsoft has this .NET framework, and they designed a functional language, F# that interacts with everything in the .NET framework. So it's easy to write F# programs and have them call out to C# or what have you, or Visual Basic even. And it fits in Visual Studio and so on. So it's a commercial functional language. And I'll show you the techniques there because that was where we tried them out. Okay, let's do something with SQL. Very simple join query. So let's find out who is younger than Alex. So here's our little database. It's got one table in it called people, and it's got names and ages, and Alex is 40, and Bert is 30, and Cora is 35, and Drew is 60. And I used to think that was old, but that's younger than me now. Oh dear. And Edna's 25, and Fred is 70. So here's our query. So this is just written out in SQL, a query language. So you say select vName as name and vAge as age. And from the people table, we're going to let U range over all the people. That means all the different rows of this table. We'll let V also range over all the rows. And then we're going to pick from uname is Alex. So pick a row where the name is Alex. And another row, V, where the age in that row is less than the age in U. That would be all the people younger than Alex. And then we're going to return, right? So V is the person who's younger than Alex. And we're going to return the name of V and the age of V. And we'll give this column the name name and the name age. So here we are. Bert is 30. Cora is 35 and Edna is 25. So those are the 3 people in the original table who are younger than Alex. Clear? Okay, any questions about this yet? Okay. I'll feel very bad if I get to the end and there are no questions, so please ask questions. Right, so we want to integrate this with a programming language. Functional languages are really good at lists. They're really good at records, so we'll make use of that. So we'll turn our table into a list of records. And in fact, a database generally has more than one table. So we're going to have a record of tables. So that's a record of lists of records. Got that? And then the entries in the records are going to be strings like Alex or numbers like age. So those are both scalars. So what is a database? It is a record of lists of records of scalars. Okay? That's what we've got here. We've got a record with one field called people, and that's bound to a list. And then each entry in the list is a record with a name field and an age field. And the values of the names are always strings, and the values of the ages are always numbers. Okay, so that is indeed a record of lists of records of scalars. Got that? Okay, does everybody see how that data structure represents that table? Yes? Raise your hands if you see it. Good. Raise your hand if you don't see it. Okay. So here's one way of doing this in F#. And you can see I've written primes next to some of these things. I've said db prime and use prime. And throughout this talk, when I put a prime on a name, what that means is I wouldn't do it that way if I were you. Okay, so this is the easy, simple, straightforward way to do it, but it's going to have some problems. So what's a database in this case, right? It has a record people, and each entry in that is a list, and each entry in the list is, the people thing is a list, and each entry in that list has a name, which is a string, and an age, which is an integer. Okay, and now we say bind db prime to this database. So that means read it in and turn it into this data structure. So we're going to read in our database from the disk and turn it into a long list of these records. Okay, and now we're going to define a function youths prime. So that's all the people younger than Alex. And what are we going to do? So that's going to take, it's going to return a list of name age pairs. And what do? We loop. So for each U in the people list and for each V in the people list, if U name is equal to Alex and V's age is less than U's age, then return, yield, a name. So you can see this is just a loop. So it loops once over the list and again over the list. So the first time U is bound successively to each element in the list. For each binding of U, you bind V successively to each element in the list. If U's name is Alex and V's age is less than U's age, then we return a record whose name field is V's name and whose ages field is V's age. Clear enough? And indeed, if we evaluate youths prime, that will give us this list with the names and ages of all the people who are younger than Alex. Okay, great, we're done. Are we done? Is there anything wrong with this? Why did I put a prime on it? Sorry? Too slow. Why is it too slow? Right. So this does a nested loop. So if people is a very long list, say there are 100,000 people, this will take 100,000 squared steps, where we'd like to do it in just 100,000 steps. So yes, it's quadratic, it's too slow. Is there anything else wrong with it? We're not actually generating a query, that's right. So it's not giving us an SQL query. Is there anything else wrong with it? It's maybe not as flexible as we want. I'll deal with that later. That's a good point. Anything else? Right, you're reading in the whole database. So I cheated, right? I showed you a database of 8 people, right? Reading in a database of 8 people is no problem, right? But real databases might have 100,000 people or 1,000,000 people. They might use up a terabyte or a petabyte or there are other funny words. What, xylobyte? We get xylobyte databases now. This would not work well with a xylobyte database, would it? Because you'd have to read in the whole thing and store it in memory, and you might have a xylobyte on your disks, but you probably don't have a xylobyte of main memory. So it wouldn't fit. So this is great, right? It's very simple and easy to read, easy to understand. There are only 2 small problems with it, right? It's too slow and it uses too much space. But other than that, it's perfect. So, how are we going to make this into something we can actually use? So here's the answer. All we need to do to make this into something we can use in practice is write some bits of it in blue. Let me show you that. So here it is with some bits in blue. And you can see that what I mean by writing something in blue is I've put some funny brackets around it. So I've put a less than at sign in front of it and an at than less sign after it. And those are called quotation brackets. Okay, how many people have encountered this idea of quotation before? Okay, a few of you, but not too many. So for the rest of you, welcome to quotation, right? Quotation is a great idea, and it's very simple, right? Inside the computer, your compiler represents your program as a parse tree, right? Your program is actually a data structure, which is the parse tree of the program. How many people understand what a parse tree is? Good. Anybody want to ask a question about parse trees? Okay. Come on, you're not doing your job of asking questions. So we want to represent the program as a parse tree inside, a data structure that represents that program. And that's all that the quotation stands for, that data structure. Okay, so when I write this and this, it means parse it as usual, but then instead of processing it as a program and turning it into the code of the program, just return a data structure that represents that program, the parse tree of that program. And you can see I did that twice, right? Up here, I've got the parse tree of a type, and then here, I've got the parse tree of a term. And you'll see it actually knows what it's parsed. So this says the database has type expr of db. Oh, sorry, I said that's a type. That's not a type. That's just a primitive built into the language. So that says call the database primitive to return a thing. And what's its type? It's an expr of type db. What does that mean? An expr that when you evaluated it, if you evaluated it, it would return a database which is a record with the people field, which contains a list of name-age pairs. And then this again is going to return an expr of a list of name-age pairs, which is going to be this answer. Okay, and we run it, and we get this answer. So how does this work? Oops. So, right, notice what I did to run it is I said, run of youths. Now, youths prime just computed a list. What is youth? It's the representation of a parse tree that returns something of that type. So what's it going to do with this data structure? So it does the following steps. Step 1, normalize the quoted expression. Now, in this case, it's already in normal form. It can't be simplified anymore, but we'll see examples where it does simplify. Step 2, translate that to SQL. So those of you who know SQL would have seen that the first query I gave you, which was SQL, and the second thing I gave you, which is what's called a computation expression in F#, and what we call a do expression or a list comprehension in Haskell, is just in one-to-one correspondence, basically, with the SQL query. So doing that compilation is really easy. So you translate the query to SQL. You actually send the SQL off to the database, and you execute it, and then you translate the answer back to the host language. So remember we said it's a very bad idea to translate the whole database because it's too big. But I'm going to assume that our answer is much smaller and that it's okay to translate the answer. How many of you are familiar with streaming techniques for getting answers from databases? Right, so if your answer was too big, you would also apply a streaming technique. I'm not going to talk about that here. And then we get a theorem, yay! Okay, and what does the theorem tells us? That each run generates exactly one query. As long as the answer type is flat, that means it's a list of record of scalars, right? It's not a list of lists. It's not nested. It's just a list of record of scalars. It only does permitted operations, in particular, no recursion, because standard SQL doesn't support recursion. And it only refers to one database, right? Because we want to translate into one SQL query. So SQL queries run against a database. So if we remember, we could right, we told it here which database we were using, the people database. So as long as everything is against that one database, we can turn it into a single query. If we had two databases, we'd need two queries, one against each database, and then some way of integrating the results. So this lets you characterize very easily, right? You could write all sorts of programs that would return things that wouldn't translate into SQL, but this lets us characterize very easily which things will. And not only does it translate to an SQL, but it translates to exactly one query. We discovered this was important when we implemented something similar in a different programming language called Lynx, which I and my team developed. And here's a great way to test your new programming language. Give it to undergraduates and say, do your project using this language. And we had one student, and his program ran really, really slowly. And we asked him, why is it running so slowly? And he said, is it running slowly? And we said, yeah. Do you know why? And he said, no. And we realized that he'd written something that would generate many queries, not just one query. So we realized that for people to have some control over how fast their program runs, they need to understand the efficiency. And the first thing in understanding efficiency is that you're doing one query, not, say, hundreds of queries. Because there are systems that will end up doing this sort of thing, but they generate what are called query avalanches, which means they do hundreds of queries rather than just one query. So knowing that you're getting out exactly one query is important. That's why we needed this theorem. So we could teach the undergraduates how to use this thing using theory, their candle in the dark, their fuzzy thing that they can hug to them. Okay, any questions yet? Yay, a question. Yes? So for each time you invoke run, it's going to generate a query and execute the query. Right? Sometimes you might actually want to separate that so that you have generating the query once and then running it many times. And again, you could do that, but I won't talk about that. Okay. And the notion here is that the database is large, so you want the time to generate the query small compared to the time to run the query. I'll give you some numbers at the end showing that for real applications, that's what happened with this technique. Good question. It's dark out there, so I can't see you. Wave your hand if you asked that question. Thank you. Okay, and then I showed you doing this in F#, but you can do it in lots of other things. So for instance, Scala has a lot of stuff in it to make it easy to implement domain-specific languages in just this way. It also supports quotation. And so in Scala, here's the naive version. You can see it's very similar. It's using a for loop with a yield, very similar to F#. And then in this case, to write things in blue, you don't need to put any special brackets. You just change the type. So the type changes from list of blah, blah, blah to rep of list of blah, blah, blah. So rep is like expr before. It means the representation of this thing. In other words, the parse tree for an expression that returns a value of this type. And so you just make that one change, and then everything is fine. So the Scala people say, it's much better, you just need to change the type, you don't need to change the code at all. And I say, well, actually, maybe it helps if you know exactly where the code is changing. So I think it's probably better to have the brackets explicit. The Scala people think it's better not to have the brackets explicit. This is an area for further research. Okay. Right, so we're halfway through, so I'm going to speed up a little bit, but I'm going to show you some of the things that you'd like to be able to do. So in fact, if anybody shows you their domain-specific language for dealing with queries, these are the things you want to ask them. Can you deal with abstraction? Can you deal with composition? Can you deal with dynamic generation? So the first thing you want to do, right, any programming language is abstract, right? We don't want to write a query just with Alex built into it. Somebody mentioned that before. So here's a query that given two ages and finds everybody older than the first age and younger than the second age. And one of those is a less than or equal and the other is a less than. So lower bounds will always be less than or equals and upper bounds will always be less than. So I can ask for all the people who are between 30 and 40 years old, for instance. And that should turn into this query, right? Select the name from people where 30 is less than the age and the age is less than 40. Is that clear enough to everybody? Questions? No. And then we might want to go, so that works, right? So it can instantiate one of these things. And the way it does it is, right, we've got here a function which expects two things, and here we're providing those two things. So you all know how to simplify this. Just we'll return this, but everywhere that A appears, we'll replace it by 30, and everywhere that B appears, we'll replace it by 40. So it's very simple substitution to do this. And I'll tell you a secret, right? This is the most important thing in Lambda Calculus. It's just how you apply a function. Take the argument. You'll have a formal argument, that's your variable in the function definition. You'll have an actual argument, that's the thing you apply the function to, and you just replace the formal by the actual, just like I've replaced A by 30. So A is the formal, 30 is the actual, B is the formal, 40 is the actual. So you replace each formal by the corresponding actual. We have a fancy name for this in Lambda Calculus to scare everybody off, right? You notice we call it Lambda Calculus to scare people off because it's a Greek letter. And then the name for this simple idea, which is you replace actual by formals, we call it beta reduction. So it's not my fault, it's Alonzo Church's fault back in the 1930s. He came up with these names. I think actually the name beta is Haskell Curry's name. Yes, the same Haskell we named the programming language Haskell after. But it was done Literally back in the 1930s, right? How many programming languages do you use designed in the 1930s? Right. So somebody say, oh, that's an old language. I want a new language. Sometimes older is better. Okay, so that's how you do that. Now we can go higher order. Okay, so now I've got something that takes an arbitrary predicate. So you take an expression that takes a function from ints to bools, and it returns a list of names. And how does it work? So it just takes a single predicate, P, and for each W in the database, if P applied to the age of W is true, then we return the corresponding name. So now we could run satisfies over a function of x that returns true if 30 is less than or equal to x and x is less than 40. And you can see that should give us exactly the same answer and should compile to exactly the same thing. And by doing beta reduction enough times, indeed, this thing will turn into the same thing as previously. So that's why it gives you the same answer. Just very simple simplification, replacing formals by actuals. So this looks all very simple and straightforward, and it is all very simple and straightforward, and most of the systems that do this, including Microsoft's original LINQ, this fails. Okay, so there are lots and lots of systems where this simple idea fails. So look for one where it works. Insist on higher order. And again, the reason this is, I think I'm going to say later. Okay, right, so you want systems where this works. And again, the reason we can make it work so naturally is because we're basing this on the theory of lambda calculus and beta reduction. So the other thing you really want to have is dynamically typed queries, dynamically generated queries. So pretty much every website in the world is just a web interface that lets you create a suitable query and then sends that off to a database and displays the results. So dynamic queries are pretty important. So here's the idea. I'm going to have a type of predicates, and these are either above an int, which means greater than or equal to that int, below of an int, which means less than that int, or and of two predicates. And then we're going to compile predicates into an expr of type int to bool. Which would be suitable for passing to satisfies. So the idea is you just look at your predicate, right, and there are three possibilities. It's either above an age, so that's the function that returns true if a is less than or equal to x. Or it's below of an age, and that's the function that returns true if the given age is less than, if the argument to the function is less than the given age. And finally, you've got and of two predicates, and what's that? You accept an age, and you want to see if the age satisfies the and predicate. So you first see if it satisfies, right, recursively now. Recursively apply P to T, and then apply that to the age, and also apply U to the age, and then just take the logical and of the results. Are there any questions about that? Now you should have some questions. Yes? Right. Why does it say lift? What is this lift about? Why do I need lift there? Because, right, this is a function. Here age is described, this a argument is of type int, right? These things in funny brackets are of type expr of bool. So this x, right, all of this really just represents a data structure inside the computer. This is just a data structure. This is an actual integer. No, we don't want an integer. We want the data structure that says, I parsed an integer here. So we're taking some real numbers and turning them back into parse trees that we can splice into larger parse trees. So that is what lift is for. Perfect question, thank you. Are there any other questions? Right, so this result is a function, and then we'll pass it to a higher order function. That is correct. I'll show you that in a minute, in fact. Good, any other questions? So it's another question. I've slipped this by so smoothly that you didn't notice. But remember I said SQL doesn't have recursion, and your final thing must not have recursion. But look, I've got recursion. How can I do that? Right, but the answer is this thing is going to evaluate fully to yield this. The recursion is not in the final parse tree I return. The recursion is to compute that parse tree. So if I compute a parse tree, I must compute a parse tree that contains no recursion. But I can use recursion to compute that parse tree. That's probably the most complicated thing I'll say this morning. Did people follow that? Okay. That's the hardest bit of theory you're going to learn this morning. Okay, so now I could say, right, what is P of and of above 30 and below 30? And it'll keep simplifying and simplifying till eventually we get this. Right, notice that in the middle, we get something that's really insane. Right, we say, okay, it's a function of x, which returns a function of x1. I've renamed it to avoid confusion. That returns true if 30 is less than or equal to x1, and then I apply that to x. So I've got lots of beta reduction to do, and similarly for the other bit. So I'm making something insanely large here, but it doesn't matter. That's what computers are for, right? You give them something insanely large and they apply simple rules. It's the beta rule, okay. Where's the actual? Where's the formal? Okay, substitute one for the other. What do I get? Oh, there's another application there. Okay, find the formal for that one, find the actual for that one, substitute that. Right, they can do that millions of times in less than a second. That's what computers are good for. So we don't need to worry about doing something that's insanely hard. It's the computer that does it. And for the computer, it's easy. Right, so now we can do a run of satisfy spliced in, and of P applied to all this spliced in. So splicing just says, this thing must compute a parse tree and splice that parse tree into the larger parse tree. That's one of the key things you do with quotation. By the way, it's called anti-quotation. So this is a quote, and this is an anti-quote. So this says produce a data structure. This says, wait, evaluate an expression that produces a data structure and put that into the bigger data structure. So this just creates the data structure for application with the result of this as the thing being applied and the result of this as the thing being applied to. And then again, after all the simplification, we get exactly the same query as before. So it's really simple and easy and straightforward as long as you've got the right theory, beta reduction, and as long as you let the computer do all the work. So Microsoft released a framework called LINQ, or LINQ. How many people have heard of that? Okay, a fair number of you. It's very similar ideas to what we had in the LINQ system and released at the same time. It's sort of the only time I've ever done research that was commercialized at the same time I was doing the research. And this is because Eric Meyer, who's a very clever guy, was working at Microsoft and led the team that developed LINQ. He came out of the Haskell community. I was basing some of what I did on earlier work of Eric's. But the Microsoft system couldn't do this. Right? The first version of LINQ, you couldn't do this. You could if you tweaked it really hard. So they wrote some blog posts explaining how you would tweak things really carefully to get this to work. But basically the answer was, this didn't work. But by applying the right theory, we can make it easy to get this to work. So this now, which had been hard, became easy. And that's why I'm showing this to all you guys, so that you know, ignore the earlier stuff they did in LINQ. Do it this way. It's not hard, it's easy. All you need is a wee bit of lambda calculus and beta reduction. How long have I got left? I have some number of minutes left. Right. So I'm going to go over this very quickly, but if you are familiar with the research literature, you will know that there's another approach to this called meta-programming. And there's something called meta-OCaml, which is designed to make this really easy to do. And what we did is we showed how you could have a language without a special type system designed for doing this, and you could still do it. So there's nothing special in F# that lets you do this, but we can still do it. Most functional languages will have some support for quotation, which will let you do this. And you don't need a special type system like the one you find in meta-OCaml. And the difference is, right, the way we did it is we used closed terms. These have no free variables, right? This was all based on X, which is closed, right? It's right here. Here's the binder for X. The way they would normally do it is they would accept X as something of type X per event and return something of type X per bool. And now this refers to X, which is a free variable. It's not bound yet. It gets bound in something else. And so now you have quotations that have free variables in them. And then to type them, you need to know what are the types of the free variables. So if you try to do this in F#, it's fine. If you try to do this in meta-OCaml, it's fine. But if you try to do this in F#, it gives you an error message, which translated says, what are you, crazy? There's a free variable in there. So the point is you can do it without using free variables. The reason people use free variables is, remember I said, this is insane. You've got all this extra simplification to do. Doing it this way automatically does that simplification for you. Right, but we can just build a tool to do the simplification. It's beta reduction. It's easy. Build the tool once, and then you don't need open quotation. By the way, right, I'm not against open quotation. It's fine if you happen to be using meta-OCaml. But what I'm showing you is you can use it even if you don't. You can use all these techniques even if you don't have meta-OCaml. That's my point. And here's the thing, right? Everybody else does it this way, right? So the real trick of the talk is don't write X per int returns X per bool, right? Returns X per int to bool. That's the trick in the talk. That's the new idea. And it was so natural going from this one to this one that I hadn't realized that we were doing something different. I just, it all works, that's nice. And I hadn't realized, wait, it's because we're not doing it this way. We're doing it this way, right? Because if we did it this way, F# would roll over and kick its legs and say, no, there's a free variable here. I don't know what to do with it. And everybody else did it this way. It was so obvious this is the right way to do it that I didn't realize we were doing it a different way. So here's a photo taken of me at the exact moment that I realized that we weren't doing the one on the bottom, we were doing the one on the top. Here I am. That's Edinburgh Castle in the background. I really literally was there at the moment that I realized this. That's me cycling to work. I got my daughter, the one you saw who made me the Smuffy, to retake this photo, and then I edited it slightly. You can guess where. Right, so why have I got this here? Oh, right. So this is, again, just what happens for the next level up. Right, satisfies gets written one way in our system, but a different way in all the other systems. So the point is, right, don't say X per A goes to X per B, say X per A goes to B. Don't say X per A times X per B, say X per A times B. And here's an interesting advantage of doing it our way. If you try to say X per A plus X per B, it doesn't work. So plus just means a value that's it's like the either type in Haskell, if you know that. And it just says it's either a value of the left summand or of the right summand. So this is the way I'd return something that's, say, an integer or a Boolean. And this works fine if your choice as to whether it's an integer or Boolean is made at compile time. But what if depending on what you find in the database, sometimes you return an integer and sometimes you return a Boolean. This won't work because this choice is in black, not in blue, and so it needs to be made at compile time, not at runtime. But this one is an actual blue runtime sum, so, sorry, it's still in black. But this one is nested inside the blue, that one's not. So this one you can make at runtime, that one you can't. So this is actually significant extra expressive power, which you lose if you use the standard OCaml technique of pushing the exprs to the inside. Okay, so the way to think about that is we use closed quotation rather than open quotation, and we put expr on the outside. We have a quotation of functions rather than a function of quotations with expr on the inside. So that simple trick makes it much easier for us to use standard languages like F# rather than have to use specialized languages like OCaml. Right. I should wrap up now, so I'm going to tell you very quickly about the other bit of theory we're exploiting here. Right, so Gerhard Gentzen wrote down the rules that we use for logic back in 1935, and I'm not going to, here's the same thing, not written in German. I'm not going to go through this in any detail, but he actually used this principle of beta reduction to simplify things. He was writing about the same time as Alonzo Church. Gentzen and Church were working at the same time. You had to wait until, they were both writing 1935, you had to wait until 1969 until Roger Hindley published something saying beta reductions are both the same thing. So what Gentzen was interested in was simplifying proofs. And so he was doing beta reduction on proofs, basically. And the reason he did it was to simplify a proof. So his idea was to make a proof that, quote, is not roundabout. And that had important consequences in logic. By doing this simplification, he could show you could prove a formula, and the only formulas you ever needed were subparts of, subformulas of, your hypotheses and your conclusion. So this meant, for instance, you could prove something about points, and maybe you use real numbers in the proof, but real numbers never appearing because you used Cartesian algebra, the Cartesian representation of geometry to do the proof. So you're using pairs of real numbers or complex numbers or something like that. But the statement is all in terms of points. The result is all in terms of points. He said you could simplify the proof so it only mentioned points. It never mentioned real numbers. So that was important in logic. But he said you can always simplify proofs, right? Here's Church doing typed lambda calculus again. And he again used normalization. And these are written out in full, the normalization rules that I use for showing you things. So the beta rule is the one at the top. X is your formal, M is your actual, and we say N with X replaced by N. That's not assignment. That's substitute for this. That thing right there in the top line. So I'm not going to go through this in any detail. If you want to learn about how this works in detail, read the textbook I mentioned at the beginning. But the point is you can write out everything you need to know in one slide. And it's all pretty simple things like, if true, then M simplifies to M. And for X in the empty list to do a loop simplifies to the empty list. And for X in concatenation of two loops, you can just do the two loops separately and then concatenate the results. And then we've applied this lots of places. Basically, this says, remember I said the answer had to be flat, and you had to refer to one database, which is flat? You can get nested things in the middle. It's fine. They will always be guaranteed to go away, thanks to this theorem that Gerhard Gentzen proved in 1935. So it says you might get more complicated data structures in the middle. They will always simplify away. So that's very important. It says, right, we have flat things that we're operating on, flat results. It can get as complicated as you like in the middle. You might have lists of lists of lists of lists of lists of age name pairs, but it will go away. Here's an example of that, which I'm not going to show you. See? 3 different things, and then you represent them very nestedly, and it all goes away. Isn't that wonderful? So the slides are there, the papers are there. You can see those if you want. Right, and then results. Here are some of the examples that we did. And you could see that before we did this stuff, some things didn't work. Right, some things work in F-sharp 2.0, some things work in F-sharp 3.0. Interestingly, pretty much everything that works in F-sharp 3.0 doesn't work in F-sharp 2.0, and the other way around. Right, but thanks to our theorem, it always works. The first reviewer of this paper says, oh, yours always works. What about the examples where yours doesn't work? And we're going, there's a theorem saying when it always works. That's why we only showed examples where it works, because everything that satisfies the theorem, it works. But they still rejected our paper. Oh, well. So anyhow, here are the times it takes us to run using our new technique, and you can see they're comparable to the times for the other systems, sometimes faster, sometimes a bit slower. And the key question is, right, wait a minute, you said at the beginning you need to normalize, right, do all these beta reductions. How long does that take? And the answer is it's a small amount of time compared to the time to execute the query. So you can afford to do this extra work because it's small compared to time to execute the query, because executing queries is expensive. Right? Never do premature optimization. Right? Something slow is fine if the other guy is slower. And that's for a different system using the same idea. And I'm going to conclude. Right, so who's heard this quote, good artists copy, great artists steal? Right, who said that? No, Pablo Picasso never said that. What actually happened is Steve Jobs said that Pablo Picasso said that. That's how the quote got to be widely known. Okay. But still, it's a great idea, right? Good artists copy, great artists steal. So normal embedded domain-specific languages are great because they steal the types of your host language and they steal some of the syntax of your host language. Quoted domain-specific languages are great because they steal types, they steal the syntax, and they steal the normalization rules. This is the really important bit. Right, that you normalize. You can write insane queries like the dynamic query I showed you that builds up this huge thing that you'd never ever write down, but normalization simplifies it to something quite sensible. So normalization, the fact that you get that for free, right? You just take the normalization rules of your system, you implement it once, and then you always have it. That's the key idea here. So, last slide, right? How does one integrate a domain-specific language into host language? Answer, oldies but goodies. Quotation from McCarthy's 1960 paper and normalization from Genson's 1935 paper. So that's it. All these slides are available online from my website. Maybe they'll put them on the BuzzConf website as well. And they're the papers to go to. This is the one I wrote on propositions as types. You can also go to the textbook on AGDA, which explains those ideas in much more detail. I'll just leave those there. Here are all the people who I worked with: Ezra Cooper, James Chaney, Sam Lindley, Cheyenne Naj, Joseph Svenningsson, and me. I worked with me. So I'll stop there. I'll just want to leave you with one idea, right? You could see how theory guided us in doing this. If we didn't have beta reduction, we would be lost in the dark without a candle, right? But beta reduction is my fuzzy friend that keeps me warm and lights the dark. So the lesson I want you to take away is that when you have a tough job to do, you should think that this is a job for Lambda Calculus. sorry. You never see Clark Kent doing this bit. There we go. Okay. This is a job for Lambda. Thank you very much.
Thank you, Lambda Man. Does anyone have any profound questions for Lambda Man? No questions?
No, I'm very sad if there are no questions.
Oh, did you, when you said it was a theorem that is only generic to one query, did you actually prove that?
Yes, we proved that theorem. It's very straightforward to prove. So the proof is like, look at all this other work you've done, now it's obvious. Sorry, the proof was to cite Gens in 1935.
Hi. Oh, that was loud. Question over here. I was wondering whether. Hello. Yes. I was wondering whether you had considered doing. Actually, I was wondering whether. Why do you pick Agda instead of something like Coq for writing the book you're writing on?
Oh, okay. Great question. Why did I use Agda rather than Coq? So there's another textbook called Software Foundations. I taught from it for 5 years. It uses Coq. After teaching from it for 5 years, I decided Coq is really well named. I just really didn't like using it. The particular problem that you have is that Coq is designed to use proof scripts, which is great if you're trying to do a really large proof, but I'm just trying to do small proofs and get the students to check their small proofs so that they know they've understood the small proof correctly. Right? It's a huge thing when the computer says, yes, it's okay. But I had to teach them not just Galena, the language for expressing things in Coq, but also the scripting language. In Agda, those two things are the same. And Agda looks much more like Haskell. So for those two reasons, I preferred using Agda. And my original goal is to just take Software Foundations, rewrite it, but transliterate all the Coq to Agda. And I started and I went, no, I don't actually like this textbook. So I wrote my own textbook. Good, great question. Thank you. Oh, by the way, I didn't mention it, but there's also a paper that you can find cited on the contents page of the textbook, which explains all this. If you want to see it written out, it's there. Yeah.
Hi. So my question is, how can you compare these quoted DSLs to like where you need some compiler magic to get the quotation going on, and DSLs based on free monads and approaches like that, where your programs are the ASTs themselves?
Right, so your question is?
Like, what are the advantages of quoted domain-specific languages against ones based on, say, free monads?
So you're familiar with a part of the literature I'm not, which is the use, I'm familiar with free monads, but I've not seen any work on free monads applied specifically to domain-specific languages. So I don't know the answer to your question, but please find me during the break or something, and you can explain to me what the domain-specific languages based on free monads look like, and then together we can work out what the comparison is. It's
Sure.
a great question. I'm sorry I don't know the answer. Right, all of you, right, never be afraid to say you don't know something. Right, it's fine. I'm feeling embarrassed, I don't know this, but there's a lot to know. It's okay not to know one or two things. So please come see me and teach me something new.
Any other questions?
Which other languages support quotation? So Haskell supports quotation. It's called template Haskell. The template Haskell is the name for the bit of Haskell that supports quotation. F# supports quotation. All lists support quotation. It's called quote. It's a simple tick mark. And then they also have, to do what's this, in the original list, it was a backtick for quote and then a comma for anti-quote. And most descendants of that, including Racket, support exactly the same notation. So everything descended from Lisp supports this. Clojure supports it. Scala supports it. I mentioned that. What other favorite language do people have? Sorry? Julia, I don't know. Good question. I do not know if Julia supports quotation. OCaml supports quotation. Meta OCaml definitely supports quotation. Any other favorite languages? Sorry? Elixir. Ooh, good question. I think Elixir does, but I'm not certain. It does. Right, Elixir does.
Any more questions? And another round of applause for Phil.